For the significant figures and dimensional analysis activity, we are basically doing sig fig problems and dimensional analysis problems. So be sure to look back over your Chapter 1 lecture handout very carefully, because all the information regarding sig figs, scientific notation, units, sig fig calculations is in there. Also, it's in your textbook, chapter 1. So a quick reminder, when looking at a number and deciding how many sig figs it contains, all non-zero numbers count. Rule 1. Rule 2, captive zeros always count. Those are zeros between non-zero numbers. Number 3, leading zeros never count. Those are placeholders. They are letting us know how small the number is. Trailing zeros count only if there is a decimal point. So in the number 0.01480, there is a decimal point after the zero after the 8 counts. The zeros before are leading, they don't count, but the zero after the 8 is a trailing zero with a decimal point, it counts. In the number 10,000 with no decimal point, only 1 sig fig. In the number 10,000 with a decimal point, that would have 5 sig figs. We encounter exact conversions and counted numbers. They have an unlimited or infinite number of sig figs, like millions of sig figs if you want to put a number in your head. If you can count the number of paper clips and it's 12, well, then that's an exact number. That would be a counted type. All the ones within the metric system, all the conversions, like 1,000 milliliters equal 1 liter, that's exact, that's defined, that's made up. All the ones within the British system that are also made up, like 3 feet are 1 yard, 5,280 feet equal 1 mile, those are made up. Those aren't based on measurement. They have an infinite number of sig figs. We often make calculations and we have to consider sig figs. When adding or subtracting, we look at all the numbers we're adding and or subtracting, and we look at how many decimals each one has. The least number of decimals determines how many we will have in our final answer. So 6.64, 2 decimals, 2.110, 3 decimals, 4.3, 1 decimal. We would type all the numbers in our calculator and the display might show 13.05, but we have to limit it to 1 decimal because of the 4.3 having only 1. So we report in the final answer 13.1. But if we were using that 13.05 within some other calculation, we would keep the 0.5, and we would have to bear in mind how many sig figs there are and take that into account in the end. When multiplying and dividing, it's a little simpler. We look at the total number of sig figs. The one with the least number determines how many are in the final answer. In this example 3, if we are taking a number, a measured number, so it has a limited number of sig figs, and we're dividing by an exact number that somehow from other information we know is exact, then that exact number does not figure into the sig figs. That is to say, it has an infinite number. So the 12 in this example has an infinite number of sig figs. So the number of sig figs we report is going to be set by 1.008 containing 4 sig figs. So we would round that number 12.096 to 12.10. And we do attach the units, grams per mole. Here's an example about rounding. If we have the calculation to make, given here 6.78 times 5.903 times 5.489 minus 5.10, what we do is we do the subtraction first, and we have only 2 decimals in 5.01, so that sets how many decimals we can have in that difference. The 5 and 5, that goes away. So we end up with 0.479, but that's only technically good to 2 sig figs. Now we keep the 0.79 as we do the other multiplying, but in the end we have to realize that 0.479 is only good to 2 sig figs. So in the end we would round to only 2 sig figs, the 19. Scientific notation, so that is a way of reporting a very big or a very small number, and it's giving the same number, but it's just doing it in a bit of an easier way. That is the number 5344000 in scientific notation. What we would do is we would move that invisible decimal point to between the 5 and the 3. We had to move it 6 places, so we report that number as 5.344 times 10 to the 6th. It's a big number, that's why we have a positive exponent. The number 0.000548, that's a small number. We move the decimal point 4 places, so to get between the 5 and the 4, so we report 5.48 times 10 to the minus 4. Just do a double check. Exponent having a negative sign means we had a small number. Positive exponent means we had a big number. And as far as sig figs go, in the number 5344000, there's 4 sig figs, so that's how many we report in our writing of it in scientific notation. So bear in mind sig figs. And of course, we can go from sig fig scientific notation to regular number. We just move the decimal point. So 4.86 times 10 to the 5, we move that decimal point 5 places and end up with the number 486000. Positive exponent means big number. 8.5160 times 10 to the minus 8, we move the decimal point 8 places toward making it a smaller number. Okay, a reminder of mathematical operations. What I want you to use is your double E key on your Texas Instrument calculator when working with scientific notation. And yet review these rules: multiplication and division, addition and subtraction. I'm sure you've seen this in a math class before, but just do a quick review so you know how to work with it independent of your calculator. But the example here is showing that double E key. If you don't have a double E key, perhaps you have an EXP key, or perhaps you have a times 10 to the n. So get to know your calculator by playing with it and putting in a number that you know what it should be in ordinary and scientific notation, and make sure that you can go back and forth correctly. Here's a section on units, all the common basic units we work with in a chem lab. Temperature, when we're converting from Fahrenheit to Celsius or Celsius to Fahrenheit, there are the conversion equations. When converting from degrees Celsius to Kelvin, there's the equation for that conversion. The metric system, which is what we use heavily in science, here it's shown at the base, that's shown by the bar, going up to deca times 10, hecto times 100, kilo times 1,000, mega, that would be 1,000,000. We see it also going down, deci, so dividing by 10, centi, dividing by 100, milli, dividing by 1,000. We have micro, we have nano. The most common ones, the ones that you'll use the most in our class, are kilo, and centi, and milli, and micro, and nano. So here's a place to find them. They are also in your textbook, Chapter 1, and in your Chapter 1 handout. A reminder, all of these conversions, those metric system ones, are exact. Alrighty, derived units, so those are when we put quantities together. Just as we multiply numbers, we multiply units. Just as we divide number, we divide units, and so forth. Density is mass per volume. We use that commonly in chemistry. Okay, our last section is on dimensional analysis, and we have some British conversions, like 3 feet or 1 yard. We have the metric ones. We just went over the metric table. Density, we're shown here, density of aluminum is 2.70 grams per ml. Molar mass, the molar mass of carbon is 12.01 grams per mole. Those are common conversions that we use in chemistry, and we will use in this exercise. So here's some examples for us to look at. How many kilograms is 24873 grams? So what we do is we start with our given quantity, 24873 grams, and we write beside it the conversion needed to go from grams to kilograms. Well, 1,000 grams equal 1 kilogram. Notice we put the 1,000 grams in the bottom, so the grams cancel out and we're left with kilograms. And whatever's in the top, 24873, and the 1 we multiply together. Whatever's in the bottom, the 1,000 we divide. The next one is, we have 34.47 kilograms, and what is that mass in pounds? So we can do it a couple ways. One way is this path A, where we start with our 34.47 kilograms, and our conversion is 1 kilogram is 2.2046 pounds. So we go directly from kilograms to pounds. Notice again the kilograms in our conversion are in the bottom to cancel the kilograms of our measured quantity. If we are using perhaps the conversion, 1 kilogram is 1,000 grams and 453.6 grams is a pound, then we would have 2 conversions. And what we do is we just set up all the conversions we need such that we're going from unit to unit to unit in a logical manner. So we start with our measured quantity, 34.47 kilograms. We write the next conversion, the kilogram to gram conversion. So we put the 1 kilogram in the bottom, 1,000 grams in the top. Next, we go from grams to pounds. So we put the grams in the bottom with 453.6 and the 1 pound in the top. And now we're going to, on our calculator, enter 34.47 times 1,000 and divide 453.6, and we'll get that 75.99. We have it as 4 sig figs because we started with 4, and our conversions have at least 4 or more sig figs. Here's our next problem. How many kilograms is 6923 feet? So we start with our 6923 feet, 4 sig figs. A conversion from feet to miles is 5280 feet equal 1 mile. Feet in the bottom, so feet cancels. Now we have miles. By the way, 1 mile is 5280 feet is exact. Okay, now we have miles. Now we can use the conversion. 1 mile, we put that in the bottom, is 1.6093 kilograms. So mile cancels, we're left with kilograms. So we multiply 6923 times 1.6093, hit divide 5280, and we get the answer, 2.110 kilograms, 4 sig figs, because our initial measurement has 4 and all of our conversions have 4 or more. The next problem is, we have a wall that is 445 feet squared, and what is this area in yards squared? So it's area because it's 2-dimensional. So we start with our 445 feet squared. Now our conversion that we know is 3 feet is 1 yard. What we have to do is square that quantity. So what we have is 1 squared yard squared over 3 squared feet squared. Notice we put the feet in the bottom and we square it, so feet squared cancels with our initial measured quantity, and we're left with yard squared. So in our calculator, we would type 445 times 1 squared. We could ignore that. And then divide 3 squared, or 9. And we would get to 3 sig figs, 49.4 yards squared. Our next problem is, what is the volume in milliliters of a sample containing 7.0113 grams of ethanol whose density is 0.789 grams per ml? Okay, so we start with that initial measurement, 7.0113 grams. Now we will use the density as a conversion, where we will put the grams in the bottom so that that cancels the measured grams, and we will be left with milliliters. So with the grams goes the number 0.789. So we have, in our calculator, we type 7.0113, divide 0.789, return or enter, and to 3 sig figs, because that's all the sig figs our density has, and density is a measured quantity. So it's going to limit us to 3 sig figs. We get our value to be 8.89 mLs. Alrighty, so the activity, we don't need to do the pre-activity. Don't submit it. Of course, you're welcome to do it, but don't submit it. Do the report for the activity. That's what you will be submitting. So put your name. Lab section does not matter. Alrighty, so note, show all calculations for full credit and pay attention to sig figs and units. So always think about reporting the correct number of sig figs and include units. Alrighty, so you're just looking in problem 1 at those numbers and writing out how many sig figs they have. Problem 2, you're doing calculations, so think about the rules for addition and subtraction, and multiplication and division. And for number 3, you're asked to report your answers in scientific notation. Okay, number 4, you're making a conversion, converting from 117 degrees Fahrenheit to degrees Celsius and Kelvin, so you'll need those equations. Yowzers, 117, that is really, really hot. Our next problem is making conversions, so dimensional analysis. It looks like that's what you're doing for a lot of the remaining problems. This problem number 9 is probably the toughest on here. It's going to involve your thinking about density, yes, and also some geometry. We have a disk with a hole in the center, so we have a huge disk and some kind of huge washer, and you are asked to work with that and come up with the volume of it. Let's see. Yes, in inches cubed. Okay, and that's the end of our lab exercise. So when you are done with all those problems, and remember to show your work, check sig figs in the end, check units. When you're done with all that work, scan it. Make sure you've scanned it as a PDF file, and then submit it in Canvas.